Yeah. The timer is set to tilt the dish with the mercury. 4.5 minutes.
Yeah, we gotta get inside and stop that timer.
Hi, quite a lot of people wanted me to do a follow-up video to this gas leakage detector teardown, which got a lot of views, and I asked in the comments there if you'd like me to see me actually doing a project, actually getting this display in here, this 5-digit 7-segment LED display to light up. And well, I'm not going to use the magic BOMB word because that could get detected by the YouTube algorithm and demonetize me, so anyway, this is what I'm going to do. We're going to do a project, actually driving this display and seeing if we can have some fun, having like a countdown timer. And there were a lot of really good suggestions in there for all sorts of stuff, like, you know, if you try and move it or whatever, movement sensor, it counts down quicker and stuff like that, and it ticks and does all sorts of weird and wonderful things. So yeah, we can call it the MacGyver project, I guess, at this stage. But if you've got a better name, leave it in the comments down below for this, a better name that's not going to get me flagged on the YouTube algorithm. So anyway, this is part one, where we're going to reverse engineer the board in here and see what the interface is, because we might as well reuse the board. Like, I could design a new board that goes in there, but what's the point? Like, we've already got the board, it's already done and dusted, so we can just design a board that actually plugs into here. But we need to know what the pinout here is and like how to actually drive this thing. So that's the point of this video, and it just sits in here, and we've already got like this nice little foam surround here like this. We've got an infrared transmitter and an infrared receiver as well, so we can actually control this remotely. And of course, there's tons of room in here for like a huge amount, like a big, large primary battery. None of that rechargeable rubbish. Even though they're LED displays, if you've got a large primary battery pack in there, it'll last for like, you know, well, a decade. Well, anyway, we can measure the current. That'll be another video, and you know, just seeing how much power this thing's actually going to take. But we've got a 5-digit 7-segment LED display there. This is part one video. We're going to look at reverse engineering this, and you can see due to the shine on the board, that means it's conformally coded. Anyway, I'm going to whack this in the do-it-yourself light box, which I'll link in up here and down below if you haven't seen it, and we'll get some high-res photos of this, and then we'll do some reverse engineering. Let's go. Okay, so we've got the board out here, and as it so happens, this is actually the second time I'm recording this, because I recorded a full 50-minute version of this video. I was going to release it, but I thought maybe it's too long, because there's probably two types of people who are watching this video. One is those that want to see like my process actually reverse engineering this, and that's what's in that 50-minute video. And there's quite a few surprises in here actually, and I'll talk briefly about them here. But if you want to see the full reverse engineering 50-minute video, I'm going to release that on my EEV Blog 2 channel, so that'll be linked in down below and up here. Go and check it out. And I'm releasing a ton of content recently on EEV Blog 2. So if you're not subscribed over there, I've already passed 100,000 subscribers, but there's a ton of content over there you're missing out on. Anyway, here is the board here. There we go, isn't it cute? And we're going to drive this sucker. So we need to reverse engineer and get the pin out for this connector up here, which is a 10-pin flat flex jobby. And as you can see here, each 7-segment display here gets its own driver chip, and these are 74HC164s. These are classic Jelly Bean serial shift registers, so these are not latched, as we'll go into in a minute. So each one of those is dedicated to a 7-segment display plus the decimal point. So we need 8 outputs, and this is an 8-bit shift register. So you feed data in, and actually this is the data input pin over here, pin 1 and 2 on the chip, and then you can see that it actually cascades out to the next, so from the previous chip out to here. So you have to feed in serially 8 bits into here and then shift it. So if you want to turn on 8 segments over here, you've got to feed in your 8 bits into this chip and then clock it all the way through until it gets over to here. And there's no output latches, so you have to blank the display, which we'll talk about shortly. But anyway, so there's not much on here. So this connector basically has clock and data for these 5 driver chips here, and we've got an infrared receiver here and an infrared transmitter LED here. This here is just one of those modules, so it's got the modulation circuitry or demodulation circuitry and everything built in, and it's just a single data line out of that thing. And we've got some filtering here. This is filtering for the digital rail, this is filtering for the receiver, and this is just some decoupling filtering for the LED drive, because they actually have separate supplies, and we might go into it. Then we've got a driver tranny there, which just drives the infrared transmitter LED here, and Bob's your uncle, right? So it's very simple now. And all this shiny stuff here, this is actually conformal coat, and you'll see in the other video had a bit of problem actually probing these. You need really sharp probes to pierce through the conformal coating, otherwise you can actually get chemicals to actually you know, strip it away either selectively or the entire board, but just sharp probes to get through. So you could come a gutser there if you don't really, you know, you could miss probing points when you're reverse engineering something like this. So a brief look at what we've got here, the 74HC164 classic Jelly Bean 8-bit serial shift register, and it does not have an output latch like you might get on, say, the 595, for example, which is much better. So as you can see here, we've just got 2 data inputs here. That AND gate just helps it for various circuit configurations, but in this particular case, you saw it there, the 2 pins were tied together, and the data just gets shifted through from the D input to the Q output on this flip-floppy here every time your clock pulse goes positive. And you can tell, you don't even have to look up the table above here, which is the state table here, to actually get this, because the clock pulse input, there's no knots on there, there's no knot on there. A knot is that little circle with an inverter, like you can see here on the MR and the master reset pin here. So you know if there's no, it's just buffering straight through into the clock, it's positive edge triggered. So on the positive edge, the data on the input pins 1 and 2 here gets shifted to Q0, and then you do another clock pulse, it gets, then whatever is on Q0 here gets shifted through to Q1 and so forth. It just gets shifted through and through until you get to the output. Now the problem with this, of course, is that when we actually want to drive this thing, when you're shifting data through, if you've got this connected to your LED display and it's on, then you're going to see this data shift through. Now, of course, you can actually shift it through like really quickly, like in a millisecond, and then you could like have it displayed for 999 milliseconds, for example, and then shift it through again, you know, however quickly you want to update the data in the display, or you can only update when it's changing. But yeah, technically, you will actually see that data shifting. So you want to actually do some sort of display blanking, usually. And the 7-segment displays, for those playing along at home, are some old HP jobbies, HDSP U113. And if we go over to here, we can actually see that, here we go. Here's the data sheet. These are HP ones. And we've got the U113, which is this one here, like this. They're common cathode, right-hand decimal, black surface. And sure enough, yep, right-hand decimal, black surface. That's exactly what we got. Now, of course, the one thing you won't find on this board are any dropper resistors for the LED display. And here is one of the first quirks with this design and interfacing with this, because we want to design a board that just, you know, interfaces over here. But it's not that simple. There's no LED dropper resistors in here. Look, there's none. So it's connected directly up to the chip. And, spoiler alert, here is the schematic. Ta-da! And well, you know, it's the pinout for this finished board here. So this is the 10-pin connector here, pin 1 here, pin 10 over here, and we've got VCC, data, and clock and ground here on 2, 3, and 4. So they all go to, the VCC goes to the rail of the chip. I don't know whether it's not 3.3 or 5. We'll talk about that in a minute because it's going to make a difference. And how we actually power this thing. So this isn't a full schematic. What I haven't shown here is that the infrared transmitter has got its own VCC. It's got its own VCC pin, and then that's actually filtered. That's got one of these filter cap. I think it's that one there, and that 47 ohm resistor there is the filter for the infrared transmitter. And then we get the data back on pin 6 here. So that's the infrared data coming back in like this. Actually, that should be IR TX on there. So what happens here, here's my original one, which you'll see in the other 50-minute video here. They've actually, this is the driver transistor over here, Q1, okay, and they're driving that. I don't know why they have a pull-down resistor there. It's kind of redundant. But yeah, pin 1 up here is actually supplying the power, separate power, to the infrared LED up here. So maybe they're actually driving those at their 5-volt rails, and the digital chip is the VCC. The VCC here is 3.3. I don't know. I haven't actually measured the main board which we've got here. So anyway, and I also didn't draw the common cathode pin there. So the common cathode pin, these are all joined together, okay? So all the displays from the common cathode pins, they're all joined together on the 5 displays, and they're going back to pin 8 here, which is the common cathode LED. So there's no dropper resistors at all on this board. So if we supplied our VCC and our ground and we did clock and data, we'll be able to shift data into here, and the displays will light up. They could be a bit bright or a bit dim, depending on how many segments we actually have turned on. Because in a good design, you would have an individual LED dropper resistor on here. And they've got room on this board. They could have added a LED dropper resistor on there. I don't know why they didn't. They've got SMD here. They could have added like little SMD dropper resistor arrays and stuff. Like, you know, price is no object for this product, as you've seen in the teardown. So yeah, so that's really piss poor design by not adding the LED dropper resistors in there. And then you could have had one LED dropper in, you know, it's not that uncommon to find just one dropper resistor in series with each display. So you could have had, like, if you didn't want 40 resistors on there, you could have had just 5 resistors and just had one series LED dropper on here. But the thing is, it depends on how many segments you turn on here as to how many segments turn on. And if you've got the one dropper resistor, well, the current has to be shared between the different segments. So if you turn all 8 segments on, including the decimal point, then you're going to get 1/8 of, effectively, 1/8 of the current that you get if you just turn on one segment, because like they're all essentially the same voltage drop. So the series resistor would be calculated on the voltage drop and the supply voltage and any RDS on the output MOSFETs inside here. But so you could do it that way, but they haven't even done that. They've just connected all the common cathodes together and taken them back here. And what they've done over here, very briefly, more detail on the other video, is this, they've got another NPN transistor here, right, which goes down to ground, and then they've just got a series base resistor there, and that's on the common cathode pin. I don't know what that part number is, what that part is. Anyway, it's basically an NPN transistor that goes down to ground with a base resistor on there. And yeah, you could actually bias that so it's like partially on. So in theory, you could actually, you know, control. It's not constant current. Okay, this is not a constant current circuit, but you could actually control the current. But as I said, all that current is shared between all 5 displays on here. 5 8s of 40. 40 different LED segments have to be shared through that one transistor there. So yeah, and this is supposed to be an outdoor readable display as well. So you would think that they want, you know, a decently high current. So I don't know how the heck they're doing it. But anyway, because this is under software control, you can actually pulse width modulate this thing. So they could be doing some sort of PWM in, but you would have to blank it when you actually shift the data in. The problem with the HC1664 is you can see the Q output here. It just goes to the output buffer. This is not designed, this chip's not designed for have a cascadable output. Okay, which some good shift registers that are designed to be cascaded, they will actually have, that pin will go out to another pin, so it's buffered, so it'll go out and, you know, cascade to other chips. But in this case, no, we have to take the output from Q7. So what we have to do here is the data has to be tapped off here for the next chip, and then so on for the next chip. But if you're driving current out of this segment here, then you're going to get a voltage drop on there, which could impact the data that's being read by the next chip. So you want to be careful with that. So what is the output resistance, output resistance of the output high side MOSFET inside these things? Well, data sheets like this for the 7.4 series logic, they won't give you, or 4000 or whatever it is, they won't give you an RDS on, because that's just not a thing. These are not designed to draw a significant amount of current, but you can actually calculate it using VOH, which is the high level output voltage here. And if we go, say, take 4.5 volts here, for example, okay, why they don't give you 5, it's really annoying. Anyway, if we got a 4.5 volt supply voltage, okay, the typical output here, we could actually take worst case of 3.98, but let's actually take the typical figure of 4.32 volts. So we can actually get our confuser out, and we can go 4.5 volt, which is the supply voltage, minus 4.32, which is 180 millivolts, 0.18 volts, and then divided by 4 milliamps, which is our output drive, which is specified for, and that's 45 ohms. So yeah, it's 45 ohms effective output resistance at 4 milliamps drive like this. But this can change depending on how many outputs are being driven and at what current it's being driven and all sorts of things. So, you know, as I said, like at worst case, if you want to take worst case, it's, you know, almost your 4.5 volts is dropped, half a volt to 4 volts here. And the thing is, here's another trap for young players, okay? If you might look at your data sheet and go, oh, look at this continuous output current. I can drive plus minus 25 milliamps. I can drive these LEDs on here. I can drive 25 milliamps per LED. Whoa, yeah, we'll really see those in daytime. Doesn't work like that. Yeah, one single output can supply 25 milliamps. But what's the continuous current? Next line here, continuous current through VCC, 50 milliamps. You can only drive 2 outputs at the full rated I/O current there. You can't drive all 8. So that's really annoying. Okay, so so when we drive this thing, okay, we have to keep in mind how much current we're taking per pin, and the whole chip can only take 50 milliamps. That's its absolute maximum ratings. So if you exceed those, you can come a gutter. Don't do it. So yeah, they're the things that we have to consider now that we've got our pin out and being able to drive this thing. We have to decide what we're going to do with the constant current LED drive here, how we're going to actually do that. As I said, you can't just hook up like a constant current circuit because, well, that's fine if you want to draw one LED, but then if you turn all 40 LEDs on, let's say you have constant current at 20 milliamps, okay, nice bright LED, right? No worries. You turn on all 40 of them, that current has to be shared. Kirchhoff's law must be obeyed. Kirchhoff's current law must be obeyed. I've done a video on that. So that 20 milliamps gets divided by 40, and suddenly you've got half a milliamp per segment, and they're just piss weak output. So honestly, I don't know how in this actual original Banshee ultrasonic gas leak detector design, how they're actually getting like all 5 displays on for like at an outdoor brightness level. Like, you know, you'd want to be driving these at like at least 10 milliamps or something per segment, and if they're like, you just can't. Even, you know, PWM isn't going to save your bacon. If you've got all those segments on, you could easily exceed the maximum current of your 164 chips. So yeah, this is a really bad design. This is really piss poor. Like, at the very least, you would have had 1 dropper resistor per you know, segment, right? So like, you'd have 5 resistors on there. For the sake of 5 resistors, I don't know what drove them to I'm here all week. What drove them to like implement it this way. It's just nuts. So we can actually get the specs here for the LED here, and you can see at 20 milliamps there, the voltage drop is 1.8 volts, and that goes down to 1.6 volts forward voltage drop at a lousy 1 milliamp here. So if we go over to what we've actually got here, as I said, we've got the 5 displays like this, which go up to the output pins of the 164s, okay, and they go directly to VCC. So let's just ignore that, you know, on resistance kind of thing, right? Let's just assume that, you know, the nice and grunty output drive, and it's going to give us exactly 5 volts or 3.3 volts output, right? And we've got 1.8 volts at either 20 milliamps down to 1. It goes down a little bit with current, but they've tied all of these pins together like this, and so we've only got the 1 pin output that we can do something with. And you just and this is what they've got on the board here, is just, they don't even have this resistor here, okay? They've just got this. And of course, if you want to shift the data, this can be used as a blank-in, so you switch the transistor off, pull this low, it's not turned on, and then the displays don't display anything, so you've got your blank in there, so you can shift in your data, and Bob's your uncle, right? But as I said, you've got 40 segments, 8 LEDs in each one, times 5, 40 of them. And as you saw in the data sheet, you can only have 25 milliamps maximum output. So let's say 20, right, to make the numbers easy. So you can have your 20 milliamps here, okay? Because you've got to, like, worst case, okay, you can't exceed that 1 pin worst case up here, okay? The 1 pin it can drive more, okay? It's not a hard and fast limit, but look, come on, right? Let's just say it's 20 milliamps though. Let's just say the magic smoke's going to be released if you go over 20 milliamps. So you can't have more than 20 milliamps coming out of 1 pin. And if you decide that you want to turn all the segments on at once, then that 20 milliamps has to be shared between 40 pins. So that gets down to 0.5 milliamps. There's no way around it. And then you've got to rely on the matching of the voltage drop, because you've got no current sharing resistors in there, even, although you effectively do. It's called the output on resistance now, So the output on resistance of the 164s is kind of like acting like a ballast resistor, as it's called, a series ballast resistor, which helps share the current. As a general rule, it's naughty to put just LEDs in parallel because they don't share current evenly. They have to be matched at the semiconductor level, and there can be differences in the doping and all sorts of, semiconductor physicsy things. But if you get them from the same batch, they're reasonably matched and stuff like that. But yeah, generally you want a series resistor in there, a ballast resistor, to at least help share the current evenly between the LEDs. But like there's no way around it. If you want to turn them all on at once, then you're down to 0.5 milliamp per segment. It doesn't matter what you PWM here. You can't just go, I'm going to PWM and drive these at hundreds of milliamps. Okay, you want to blow the output of your 164? Go for it. And even if you do some constant current circuit like this, constant current dummy load, I've done the video on that. It's very popular. Everyone's almost certainly seen it. Even if you do constant current, it makes no difference. I mean, it's just, there's nothing going on here. Now, it might help, of course, to power the 161s from 3.3 volts instead of 5 volts, because they can work, HC series can work down to 2 volts, so no worries there. So what value do you have to drop a resistor down here for 1 segment? Just 1. If you power it from 3.3 volts here, then you've got the ballast resistor up here, but let's just ignore that. Let's say you've got 3.3 volt supply as a 3.3 volt supply minus your 1.8 volts on your LED. So what does this resistor here have to be? Well, let's say you want 20 milliamps current flow, then divide 20 milliamps and get your confuser out, work out that, and that's equal to 75 ohms, like that. So yeah, so you want a 75 ohm resistor in there to give you that nominal 20 milliamps at 3.3 volts, ignoring any drop in your 161. But then, as I said, you start turning on the other segments and the current must be shared. Kirchhoff's current law. Yeah, so this kind of really sucks. We're sort of stuck with a meh display. So I don't know, the only other way to do it would be, well, not turn on all 40 segments at once. They might actually be multiplexing the displays. You could actually multiplex them. You might go, well, okay, let's multiplex 1 display at a time, and then you're just constantly shifting stuff all the time. You blank, shift, blank, shift, blank, shift, and then, and then turn on, you might turn on each one of these for 100 milliseconds or something like that, 200 milliseconds, for example. You might turn on each one of these digits and then shift in the data real quick. So I think that's really the only way forward, really, is to multiplex these displays to ensure we don't have all 40 on at once, and to if we can limit it to one segment, one display at a time, then we've reduced our complexity, our problems by a factor of 5. So one fifth the problem. So then we could easily, you know, but yeah, if you just have them all at once with 40, you're screwed. There's nothing we can do, really. So yeah, so if we want to use this actual display, unless we redesign it or bodge it in with dropper resistors or whatever, then yeah, I think we're probably going to have to drive, you know, if we want decent brightness out of it, we're going to have to drive like one entire segment and then multiplex it. And that makes it more complex and interesting, I guess, especially if you're doing it with discrete logic. But yeah, cool, huh? So anyway, we want to do a project reusing this board. So yeah, we have to deal with this thing. So we've got to decide how we're going to do that. Leave it in the comments down below how you think we should best approach this. I know there's people that say just respin this board, just respin it. What's the big deal? I think it's the principle of the thing that we want to reuse it. Anyway, thoughts and comments down below, please. And I want to know which direction you want me to take this project. We were just talking about this on the Amp Hour this morning with Chris Gamble, and we can go several directions. In fact, we don't have to pick one. We can pick multiple. We can do multiple projects. You can have one project over here, which is all discrete. We can drive this discretely using discrete 7/4 series logic, or we could, well, that's option one. We could do option two, which is use a PLD or an FPGA or something like that to actually drive it. Once again, you're using discrete gates to actually do that. Option three is just throw any Joe Bloggs microcontroller. Do you want to see the 3-cent Paduk? Do you want to see a bloody ARM thingamabob? Do you want to see a PIC? Do you want to see an AVR? What do you want to see? And an interesting fourth one, which was brought up on the Amp Hour today, was that we could do like that Raspberry Pi microcontroller. That new jobby, not the Raspberry Pi itself, but the microcontroller version was RP40 something thing, and that's actually got logic output, like a little configurable thing of logic output. So maybe this might be an interesting project for something like that. So it's not just entirely software driven. We're kind of like doing a little hardware output thing. Let me check the datasheet on it. Yeah, here it is here. There are two identical PIO blocks. Each PIO block has dedicated connections in the bus fabric. So yeah, okay, so we've got like state machine 0. So they've got little state machines here. Looks like they've got 4 state machines, and then you can map those over to GPIO, just your regular IO outputs, you know. So maybe we could do something like that. I don't know. Anyway, leave it in the comments down below how you want me to take this project. I may, of course, decide to ignore the crowd and just do my own thing, whichever interests me, but no, please leave it in the comments down below. If you got, where do you think, like if everyone says I should take it in a, discrete, 7/4 series logic, and we can just drive it with 7/4 series logic, or and no Internet of Things wankery, please, no freaking Wi-Fi bullshit either, no, none of that rubbish, right? I just want to drive this thing and maybe have a couple of, interesting things like a tilt thing if it, counts down faster if you tilt it or rock it. Anyway, leave your ideas down below what I can do with this thing. So anyway, hope you liked that video. As I said, there's a 50-minute version of this, which basically is me going through reverse engineering this and going through a bit more detail in the data sheets and other design aspects and stuff like that. Because this was interesting. When I find it, I assumed that this thing was designed a certain way, and it wasn't. I did not see this coming. That it would have common cathode, all this, and then be driven over here. And it's just, very interesting. Anyway, if you like it, give it a big thumbs up. As always, discussed down below. Catch you next time.